Hello students, this is Ms. Riggins with today's video, and we're on the topic of power functions, which is in chapter 11, section 1 from your textbook. Before we talk about power functions, let's talk about some type of popular relationships between two quantities. The most popular and i.e. easiest relationship between two quantities is directly proportional or proportional. And you are familiar with them for linear functions because every linear function um, starts off with a directly proportional relationship, or the parent function, and the relationship between that looks like this. If I have two variables, y and x are directly proportional when y can be found by taking k, which is a constant, and multiplying it times x to the power of n, which is also a constant. And it's important to know that in this case, n has to be greater than 0 in order for it to be a directly proportional relationship. So let's take a look at an example. An example for directly proportional is your pay rate. Let's say you make $8 an hour. So the relationship between your hourly pay, between the number of hours you work and your pay, the amount of money you are paid, i.e. earned, is a directly proportional relationship. Okay? And sometimes people won't say directly proportional, they'll say proportional. So your pay is proportional to your the number of hours you worked. Then we have another concept called inversely proportional, which is this relationship between two quantities is when one quantity can be found by dividing a constant by a power of x. And that's in this situation. And we call this, in this case, y is inversely proportional to x. And in this case, k and n are all constants, but n has to, again, be greater than 0. So an example of inversely proportional is, let's say I'm at a party and I order enough pizza for 37 slices, and I'm trying to figure out how much each person gets to eat. And so what I do is, that's an inversely proportional relationship. I would take the number of slices total, which is 37, divided by the number of people at the party. And that will tell me how many slices each person gets. So the more people that are at the party, the less number of slices each person gets. Or whereas in comparison to directly proportional, the more hours I work, the more money I get paid. Now, they all have in common, both directly proportional and inversely proportional, that they involve a constant and a power of x. And if you notice, if I work no hours, I get no money, no matter how large my constant is. If there is no one at the party, there's no way for me to just specify how many slices. So each of these also has the condition that the point 0, 0 has to be part of each of these relationships between your x and your y. So why is that of any importance? Well, let's take a look at a new type of function called a power function. And a power function is of the form k times x to the p, but in this case, p doesn't have to be greater than 0. P can be positive or negative. And k, of course, is also another constant. So why is this of any importance? Well, this is a functional relationship, so every input has only one output, but also it also passes through the point 0, 0. And we can basically combine two situations into this one situation of a power function. So let's take a look at this. This is a line that passes through 0, 0. So that lets us know this is a directly proportional relationship, because a linear function is a number times the input will give you the output. And since it passes through 0, 0, that means it's directly proportional. Well, let's see what happens when I change that constant of variation. If I make the constant larger, then that means that the graph changes its slope. When I make it smaller, the graph changes its slope as well. But what if we don't have a line? So let's make k be equal to 1. Oops. Okay. And let's change the power of p. When p is 2, we no longer have a linear function, we have a quadratic function. When p is 3, we no longer have a quadratic, we have a cubic. And when p is 4, we no longer have a cubic, we have something that looks like a quadratic. But actually, another way to look at this is it's also described as when x is to the 4th power. As we can see here, p is 4. So as I go to the 5th power, it looks very similar to when p was equal to 3. And that's because when p is an even power, like 2, 4, and 6, we have what looks like a parabola. And when p is an odd power, greater than 1, we have something that looks like a cubic function. Okay? So you should now be able to fill out the table on the notes. And you guys can do that on your own by filling in what the shape of the graph looks like for each of these. And if you want to, come up with the rule for even and odd functions. Now let's take a look back at a situation where p is no longer a positive number, but a negative number. So let's move this down. And now we're at -1. So that means the graph changes. We no longer have parabolas or little cubics. We have, looks like, two different pieces of graphs. And that's because this graph has two asymptotes, a horizontal asymptote where it cannot cross, and a vertical asymptote where it cannot cross. Let's see what happens when, in this case, the horizontal and vertical asymptotes are at the x and y axis respectively. Let's see what happens when I change p to a -2. Now we have again two different graphs, two different pieces of the graph, but they all cannot pass the cross the y-axis, and the asymptote is a little bit different. Let's go to -3. Now we're back to two opposite sides. And when I change it to -4, we're back to a different set of graphs here. So it seems to note that when p is a negative even number, we have these two branches, or which we call them, basically hugging the positive y-axis and having an asymptote at the x-axis. And when we have p being an odd number, we have the two branches on opposite ends. And that's when p is negative. So you should be able to fill in the chart. You can fill in the chart as we see here on the notes with the asymptotes that we have as well. And now let's take a look at what happens when p is no longer a whole number, but what happens when p is a fraction. What's going to happen there? Well, let's see. So here p is 1. Let's see when we change p to 1.25. Let's look at what happens when we change p to 3/4. Let's see what happens when we change p to a half. They look to be very logarithmic in nature. Let's see where we change p to 1/4. I mean, 1/4. Okay, so what happens is, in between, these function values are getting closer to the next biggest whole number. So in this case, 2. So here we go from linear to somehow to be quadratic. So as we move up, it's like the graph is curving to become quadratic. So what I would like you to do is try desmos.com/calculator to see what the domain and range of these graphs are when p is a fraction, and see if you can develop a relationship between the two. Okay, that's it. I'll see you guys in class.